Hey everybody, welcome back to my podcast, Anatomy and Physiology Bit by Bit. This is your host, Dr. Steve Sullivan, coming to you from just outside of Philadelphia, where I teach anatomy and physiology at Bucks County Community College. All right, so welcome back. This episode, we are going to focus on hearing. So there are two senses associated with the ear, hearing and equilibrium. And in this episode, we're just going to focus on hearing because that's enough. It is a pretty big topic, much like vision. And then we're going to tackle equilibrium in the next episode next week. So we'll stick with hearing. Hearing is a really interesting thing because it deals with the physics of sound waves. And just kind of like I like talking about the physics of light when we talk about vision, I like talking about the physics of sound when we talk about hearing. We've got these sound waves that are making their way into our ear and causing a series of vibrations that I'm going to explain later on that ultimately lead to an electrical stimulation of a receptor. So I'm a big fan of these topics. Sensation is probably one of my few favorite chapters in the A&P textbook that I use. I do think it's really interesting the way we respond to the world around us, the way we perceive the world around us, and also the way we respond to the universe inside of us, because the sense organs that we have are not just about vision and hearing and smell and taste and touch. They're also about the chemical composition of what's inside our bodies. So we need to be aware of our blood pressure. We need to be aware of our intracranial pressure. We need to be aware of our hydrogen ion concentrations. We need to be aware of our carbon dioxide concentrations, our insulin levels, glucose levels, electrolyte levels, all of those things. We have receptors for all of them so that our bodies can have a good idea of what's going on. So if something needs to be changed, we can change it. And that's homeostasis, right? That's basically our body's ability to maintain a fairly constant levels of controlled conditions inside our bodies, even though we live in a world and universe that is throwing variations at us all the time, right? So if we didn't have thermoreceptors, how would we regulate our body temperature, right? So you can't tell someone how to get to your house if you don't know where they're starting. So we can't fix our body temperature if we don't know what our body temperature is. So it's really interesting sensation, and we're almost done with it, right? We've got one more episode after this that's sticking with sensation because we do need to also know about our body's position in space and whether or not we're moving and how fast we're moving and in what direction we're moving. Like, we need to know these things. So if you were to trip over something and you put your foot out to stop yourself from falling, how would you know where to put your foot if you didn't know which direction you were falling and how quickly? So all this stuff I find extremely interesting. I'm kind of hoping you also find it interesting. And having said that, I think it's time to get to it and talk about hearing. Okay, so let's start by talking about the anatomy of the ear. There's a lot of parts to the ear, and some of them are for hearing and some of them are for balance and equilibrium. But I want to go through like the general anatomy of the ear first. You probably know that the ear is divided up into three sections: the external or outer ear, the middle ear, or the inner or internal ear. So the outer ear or external ear is the part that you can see, right? So you've got this big cartilaginous skin-covered flap outside your head that looks like the reverse side of a trumpet. And that's the external ear. It consists of the auricle, which is also called the pinna, and that's the actual trumpet end that's collecting sound waves. And that is covered with skin, and it's divided up into two sections of its own. The rim of it is called the helix. That's the part that's up on the top. And the bottom is called the lobule or lobe, and that's the part that you might put a traditional earring in. That is part of the auricle or pinna. And then you'll notice, obviously, that there's a little piece of cartilage flap coming from the front, sticking back toward the back of your ear, and that is called the tragus. That little piece of cartilage, that hard piece of cartilage, is called the tragus. Sometimes I see an earring in there too. And then obviously you'll know that there's a hole in your ear. And that hole is called the external auditory canal. So you may remember from doing your skull studies that we had a hole in the temporal bone called the external auditory meatus. That is the entrance to the canal. Now, we call it the internal auditory canal when it's just in the skull. But when you can see it covered with skin, and you can see it from the outside through the auricle of your ear, that is the external auditory canal. It's about 2.5 centimeters, and it's curved, and it runs through the temporal bone toward the tympanic membrane, which is called the eardrum. We also know that inside your ear are ceruminous glands, which you may remember from a previous episode when we talked about the skin. Ceruminous glands are integumentary glands, and they produce earwax. They actually produce a waxy substance that combines with epithelial cells that are shedding off of your ear skin, and that forms what we call cerumen, or earwax. They're specialized sebaceous glands, and they have some insect repellent qualities as well that prevents most insects from even wanting to enter your ear. Now, for the most part, the cerumen usually dries up and falls out of your ear, but sometimes people produce excess amounts of cerumen, and it impacts on the eardrum and becomes like attached to it. We call it impacted cerumen, and it muffles the sound. It can even cause pain and inflammation in there. This is why you're really not supposed to stick a cotton swab or a Q-tip in there, because you're not really pulling earwax out. You're actually pushing earwax in when you do that, and that's not good for you. All right, so then once we get past the tympanic membrane, on the other side of the tympanic membrane, we're going to be inside the middle ear. The tympanic membrane is technically part of the middle ear, but it is this thin translucent partition that divides the external and middle ear, but it also vibrates when sound waves hit it. And the middle ear is small and air-filled cavity. It's inside the temporal bone, and it's also lined with epithelium. So that tympanic membrane forms the external wall of the middle ear. On the other side of the middle ear, you're going to see two other membrane-covered openings called the round window and the oval window, and they lead to the inner ear. So we'll get to that in a minute, but also inside that middle ear are the three smallest bones of your body. They're called the auditory ossicles. They extend across the middle ear, and they're attached to the middle ear by ligaments, and they're attached to each other as synovial joints. So these are actually movable synovial joints between the auditory ossicles. Now, there's three of them, so we're going to name them from the one that's closest to the eardrum or tympanic membrane to the one that's closest to the inner ear. So we start with what's called the malleus, also known as the hammer, because malleus is Latin for mallet or hammer. It's attached to the middle ear side of the tympanic membrane, the interior surface of it, and it articulates with the body of the next bone called the incus. Now, incus is Latin for anvil, so it's almost like a hammer hitting an anvil when we vibrate those bones. And the anvil articulates with the next bone called the stapes, which is Latin for stirrup. So it looks like what a cowboy might put their foot in when they get on a horse. So it's kind of like this rounded area with a flat foot plate. And we call that bone the stapes, and that bone fits right into what's called the oval window. The oval window is the entrance to the inner ear. So we're going to vibrate all of these bones and then create vibrations in the oval window so that we can transmit them to the inner ear, the internal ear, and specifically an organ in the inner ear called the cochlea, which is our sense organ for hearing. There's also another window in there called the round window, and the round window is just another opening to the cochlea, but it's actually the end of the cochlea. So not only do we have bones in the middle ear, we have muscles in the middle ear. There are two tiny muscles that attach to the auditory ossicles. They're called the tensor tympani muscle, which limits movement and increases tension on the tympanic membrane to prevent inner ear damage due to loud noises. And it's innervated by the mandibular branch of the trigeminal nerve, which is cranial nerve 5. The stapedius muscle, as you can imagine, attaches to the stapes. So when the stapes is vibrating, the stapedius muscle contracts to kind of limit those vibrations a little bit so they're not going to damage the oval window. That's what we don't want. This decreases our sensitivity to hearing. So if you have a paralysis of the stapedius muscle, then what can happen is you can end up with something called hyperacusia, which is abnormally sensitive hearing. And you don't want that. That can be really, really problematic. It takes a second, or really takes a fraction of a second, for these muscles to contract. And so they're good at protecting us from prolonged loud noises like a siren or something like that, but not for brief loud noises like an explosion or a gunshot. So they do protect us, but they're mostly protecting us from really loud music or things like that, not from sudden loud noises. There's also a tube that begins in the middle ear and leads to your pharynx, specifically your nasopharynx, the upper portion of your pharynx, which is your throat. This is called the auditory tube, also known as the eustachian tube. So it connects the middle ear to the nasopharynx of your throat. It's normally closed at the pharyngeal end, except for when we're like yawning or swallowing. And what it does, it allows for pressure to be regulated between the middle ear and the external ear, which would be the atmosphere around us. So when the pressure is equal between those two areas, the eardrum or tympanic membrane can vibrate in response to sound waves so that we can hear. But when the pressure is not equal, what can happen is it can get in the way of the vibrations of the tympanic membrane. So it won't vibrate as easily if there's not an equal pressure on either side. You can get pain from that. You can get hearing impairment. You can have tinnitus, which is also a ringing in the ears, or sometimes you can get vertigo, which is like a dizziness. That's actually a problem with the pressure. But you'll notice, if you've been on a plane or something like that, that if you yawn or swallow or chew while you're on the plane, you can equalize the pressure because you keep opening the pharyngeal end of that tube and allowing air to get up in there. And if the pressure is really great on the outside of the ear, it's going to push the tympanic membrane in toward the middle ear. But if you open your mouth real wide, like you're yawning or you're chewing gum or something like that, then you're going to keep opening up that pharyngeal end and allowing air from your throat to get into the middle ear and push the tympanic membrane back out so that it's equal pressure. So we call that equalizing the pressure. And that's something people do. Sometimes scuba divers, when they go down low and the water pressure is pushing their eardrums, they hold their mouth and nose closed, and then they try to force air up into that auditory tube, and that equalizes the pressure as well. All right, we also have the inner ear or internal ear, and it's known sometimes as the labyrinth. There's two main divisions of the labyrinth. We have a bony labyrinth, which is basically just a series of cavities in the temporal bone, and we have the membranous labyrinth, which is a series of sacs and tubes containing fluid called endolymph that are inside the bony labyrinth. It's kind of like a tube inside a tire. So if you have a tire on your car, the hard rubber that touches the road is the bony labyrinth, and then the tube inside of that holds all the air, that's the membranous labyrinth. The endolymph that fills the membranous labyrinth is actually more like extracellular fluid than intracellular fluid in that it is rich in potassium ions and helps play a role in the generation of auditory signals and vestibular signals. So that labyrinth has three different regions. One is called the semicircular canals, and that is the area where we're going to have receptors for equilibrium. One is called the vestibule, which also has receptors for equilibrium, and the other is called the cochlea, which has receptors for hearing. The bony labyrinth has perilymph, which surrounds the membranous labyrinth and is kind of similar to cerebrospinal fluid. For the inner ear, I'm going to go into the specifics of the anatomy based on which sense we're talking about. So I'm going to split off now into hearing, and we'll talk about that, and I'll describe the anatomy of the cochlea as we go. So what is hearing? Hearing is our ability to perceive sound. And in order to do this, we need to convert sound waves into electrical nerve signals. So I want to talk about how sound waves travel, how they enter our ears, and then we'll talk about how they're transduced into an electrical stimulus so that we can get a nerve signal going to our central nervous system and perceive a sound. But sound is a specific physical thing, right? So sound is the movement of air molecules. So when you hit a tuning fork, for example, or when you talk and your vocal cords vibrate, when those structures vibrate, they push the air molecules next to them into other air molecules. So consider that two pieces of matter cannot occupy the same space, right? So that includes air. Air is matter. Air molecules are basically molecules of nitrogen, hydrogen, oxygen, carbon dioxide, water vapor, and other things. So those molecules can't exist in the same space as other molecules. So if I vibrate my vocal cords, then that vibration, that moving of the vocal cords, even the tiny, tiny bit that they're moving, pushes air molecules next to them into other air molecules. And then those air molecules get pushed into the air molecules next to them, and so on, and so on, and so on, creating waves that we call sound waves. Basically, air molecules moving in a wave-like pattern through the air. Or the water, for example. It could be water. Sound moves through multiple media. So when those air molecules that are vibrating and moving because of the vibration, when they get to your ear, they're going to make their way into the external auditory canal and reach the tympanic membrane. And then the air molecules pushing against the tympanic membrane will push it. And it will vibrate in response to the vibrations that caused air molecules to move, the sound waves. So now that vibrating tympanic membrane is going to cause the first auditory ossicle to vibrate, and that's the malleus. So the malleus will vibrate in response to the tympanic membrane vibrating. And remember, it is attached to the incus by a synovial joint, and so that will cause the incus to vibrate. And then the incus causes the stapes to vibrate. So those three auditory ossicles in a series of steps are going to conduct the vibration of the tympanic membrane that was caused by the sound waves in the air. Now, sound waves have a frequency, meaning that how quickly sound waves come one after the other is the frequency, how frequent the waves hit the tympanic membrane. And the higher the frequency, the different the pitch. So a higher pitched sound is a higher frequency, and a lower pitched sound is a lower frequency. All right, here's a good example of how sound waves work. So the length of a sound wave, the distance between the first movement of the molecules and the next time the molecules move, is called the wavelength. And the frequency is how many times the wave happens in a certain period of time, right? So per second, let's say. And that's called the frequency. So the frequency and the wavelength are inversely proportional. The longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. So the Doppler effect is what we hear when a train, for example, is coming toward you, and you hear the train whistle getting higher and higher in pitch as it gets near you, and then getting lower and lower in pitch as it gets further from you. Take a listen to this. What's actually happening here is as the train whistle is vibrating and making sound. It's creating movements in the air molecules in waves. So it's pushing air molecules toward you when the train's coming near you. But also the train is moving at the same time. So each sound wave that the train whistle is producing is closer to the last one that it produced than it would have been if the train was standing still. That increases the frequency and shortens the wavelength. So the pitch is going to get higher because the higher the frequency, the higher the pitch. The closer and closer the train gets to you, the higher and higher the pitch is going to sound. Now, when the train passes you, every time that whistle puts out a sound wave, the train moves away from you, making the wavelength longer than it would have been if the train was standing still. So the pitch goes down the further the train gets away from you. So that's called the Doppler effect, and it's a really good example of how sound waves work in terms of being physical things that are happening in the air, moving molecules of air in a wave-like pattern.
Bombas makes the most comfortable socks, underwear, and T-shirts.
Warning, Bombas are so absurdly comfortable you may throw out all your other clothes.
Sorry, do we legally have to say that?
No, this is just how I talk, and I really love my Bombas.
They do feel that good, and they do good too. One item purchased equals one item donated.
To feel good and do good, go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
All right, so that vibration from the three auditory ossicles makes its way to the oval window, which is what the stapes is sitting in. And the other side of that oval window is the cochlea. The cochlea is the sense organ for hearing. And the cochlea is divided into three chambers, each filled with fluid. The scala vestibuli, the cochlear duct, and the scala tympani. Those are the three chambers. The two scala are filled with perilymph, and the cochlear duct is filled with endolymph. So the scala tympani and the scala vestibuli are surrounding the cochlear duct. So it's a unit of three chambers. The one in the middle is the cochlear duct, and on either side of it is a scala. The scala vestibuli and the scala tympani. The oval window enters into the scala vestibuli. Now the scala, again, they're filled with perilymph, but the cochlear duct is filled with endolymph, which we talked about earlier, was that high potassium substance. So the footplate of the stapes sits in that oval window, and when the stapes vibrates, so does the footplate, and it causes waves in the perilymph inside the scala vestibuli. Those waves cause a vibration on the floor of the scala vestibuli, which is called the vestibular membrane. And that causes waves in the endolymph of the cochlear duct, because the vestibular membrane is not just the floor of the scala vestibuli, it's also the roof of the cochlear duct. So the movement of that vestibular membrane will create waves of endolymph in the cochlear duct. Now, the floor of the cochlear duct is called the basilar membrane. And on the basilar membrane is the spiral organ. This is the part of the cochlea that has the auditory receptors in it. So these are going to be responding to the vibrations of that basilar membrane. All right, let's talk about that spiral organ a little bit. It's also called the acoustic organ or the organ of Corti. It consists of rows of auditory receptors, which we call hair cells, and it also has supporting cells and a gelatinous roof called the tectorial membrane. The supporting cells are basically what allows the hair cells to stand up and physically be there. The tectorial membrane is above it, and the hair cells, which are basically stereocilia sticking up off of the hair cell, they hit the tectorial membrane at their top. So the basilar membrane vibrates and pushes the spiral organ up into the tectorial membrane. Those stereocilia of the hair cells are going to bend. Now here's the thing that people don't realize sometimes. Even though they're called stereocilia, they're actually microvilli. They're not cilia, they're microvilli. And because they're microvilli, they have mechanically gated ion channels in them. And when those ion channels open, we can see movements of ions across the membrane and into the cell. All right, so remember, these stereocilia, they're sitting upward on the apical surface of the hair cells, which are the auditory receptors. And when the basilar membrane vibrates, that acoustic organ is pushed up and down. And every time it goes up, the top of those stereocilia hit the tectorial membrane and bend. Now again, like I said, those stereocilia have mechanically gated potassium ion channels in their plasma membranes, and each stereocilium has a stretchy protein fiber called a tip link that's attached to its lateral side and to an ion channel of an adjacent stereocilium. So try to picture that. You've got these stereocilia sitting straight up, and then attached to each one is a little protein chain that reaches over and also attaches to the stereocilium next to it, like a tightrope but on an angle. And it's also not only attached to the stereocilium, but it's attached to a mechanically gated ion channel on that stereocilium. So when the stereocilia bend, the tip link tugs on the mechanical gate of the ion channel, causing it to open. Now remember, endolymph is like intracellular fluid, which means it has a high potassium ion concentration compared to the inside of the auditory receptor cell. So when that potassium ion channel opens, potassium ions will flow down their concentration gradient into the receptor cell. Now they're positively charged ions, so they will depolarize the membrane of the auditory hair cell. Now these are separate cells, which means they're not dendrites of the sensory neuron for auditory. So their local potential is going to be a receptor potential. And if the receptor potential is strong enough, it is going to release a neurotransmitter to the dendrites of the cochlear nerve. The cochlear nerve is half of the vestibulocochlear nerve, which is known as cranial nerve 8. Cranial nerve 8 is the vestibulocochlear nerve. It has two branches, the cochlear nerve and the vestibular branch. The cochlear nerve is for hearing, and the vestibular nerve is for equilibrium. So we're focused on hearing right now. So we'll talk about that. So those neurotransmitters that get released from the auditory hair cell are going to then create a local potential on the dendrite of the cochlear nerve. That local potential is going to be caused by the opening of a ligand-gated ion channel because this is a neurotransmitter. It's a chemical. So the postsynaptic membrane in this particular synapse we're talking about is the cochlear nerve's dendrite. In that membrane, we've got ligand-gated sodium ion channels, and the neurotransmitter being released by the hair cell is the ligand. So that ligand stimulates a receptor. The ligand-gated ion channel is open. It's a sodium ion channel. So sodium ions flow down their concentration gradient, which means the net movement is into the cochlear nerve cell. That is going to depolarize the membrane. So we're creating an excitatory postsynaptic potential. Think way back to when we talked about chemical synapses. This is an excitatory postsynaptic potential, or an EPSP. If it's strong enough to reach threshold, then we open up voltage-gated ion channels and we get an action potential in the cochlear nerve. And if that happens, those action potentials tip like dominoes all the way down the cochlear nerve, and we have a nerve signal. And that nerve signal is going to make its way all the way to the central nervous system, the cochlear nerve being the first-order neuron of hearing. So this is how we transmit sound waves into electrical nerve signals. Using the cochlea, using the tympanic membrane, using the auditory ossicles, right? Sound waves being collected by the pinna or auricle of the ear. Now we want to look at the projection pathway, which means what is the path that this nerve signal is going to take to make its way to the central nervous system so we can perceive the sound we're hearing. Now again, the cochlear nerve is the first-order neuron of hearing. Now, if you remember back when we talked about the somatic sensations, we discussed first, second, and third-order neurons for sensation. Well, for hearing, we have 4. There are 4 neurons that we have to take to get to the central nervous system. So 4 orders of neurons, not 3. All right, so let's think about what happens now. When you hear something on the left side of your body, it takes place on the left. You don't just hear it with the left ear, you hear it with both ears. So you're going to get information from both ears reaching your central nervous system from the same sound. Now that brings something else into play. In terms of the physics of sound, sound travels at a specific speed through the air. And it's not that fast. We have planes that fly faster than the speed of sound. Compare it to light, not even close. So sound travels at a specific speed. It's not that fast. So the sound you're listening to gets to each ear at a different time. And we're going to use that time difference to estimate where that sound is happening in space around our bodies. All right, so each ear sends nerve fibers to both sides of the medulla oblongata of the brainstem. And that location is called the cochlear nuclei. So the cochlear nerve, you got a left and a right cochlear nerve, you got a left and a right ear. So those cochlear nerves are going to lead to what's called the cochlear nuclei. There, the cochlear neurons synapse with second-order neurons that ascend the brainstem to the superior olivary nucleus of the pons. The superior olivary nucleus functions in binaural hearing, which means comparing signals from the right and left ears to identify the direction from which a sound is coming. Now, we don't just perceive a sound, right? So when sound waves hit our ears and stimulate nerve signals, there's more to us hearing something than being able to identify what it is. So other fibers from the cochlear nuclei send nerve signals to the inferior colliculi of the midbrain. So if you recall the midbrain, part of the brainstem, the colliculi are in the posterior part of the midbrain. And there are 2 sets. There's superior colliculi and inferior colliculi. We're going to send nerve signals to the inferior colliculi of the midbrain. And they are going to help locate the origin of a sound in space. They're going to also process fluctuations in pitch, and they're going to integrate reflexive movements of the head and neck in response to loud noises. So if you are sitting in your room studying, and there's a big loud crash in the hallway, and you all of a sudden you jerk your head to the direction of the noise, that is a reflex that is integrated in the inferior colliculi of the midbrain. And it's in response to auditory stimuli. All right, so third-order neurons begin in the inferior colliculi, and then they go to the thalamus. Now, we know what the thalamus does. The thalamus relays sensory nerve signals to the correct part of the cerebrum so that we can get conscious awareness and perception of those sensory nerve signals. So the thalamus is the next stop. And in the thalamus, those neurons synapse with the fourth-order neurons, and they're going to travel to the primary auditory cortex in the superior margin of the temporal lobe. It's deep, deep, deep within the lateral sulcus, which is the space between the temporal lobe and the parietal lobe. This is the site of conscious perception of sound, and it completes the information processing essential for binaural hearing. In this location, we can also compare the sounds we're hearing to memories of previous sounds that we've heard and try to identify the sound. So it's one thing to describe the sound. If it's a voice, or if it's the sound of a particular song, or if it's the sound that your washing machine makes, or something like that. It's one thing to describe the sound. It's another thing to compare what you're hearing to sounds that you've heard before, because you have to have a memory stored of that. So I've mentioned this before. Our nervous system is a big collaborative effort of lots of different parts. And you've got to access memories, and you might hear a sound that's a song that reminds you of somebody, and you might have an emotional reaction. There's a lot of things happening with sensation that go beyond just knowing what's happening in the world around you, right? Identifying a sound. So you might hear a sound that sounds like water dripping, and that causes you to get up and check and see if there's a leak somewhere in your house. You might hear a sound that sounds like water dripping, but you know that's what it sounds when your washing machine's on, so you don't really even bother with it, right? So you're going to have reactions to sounds that are beyond just recognizing a sound. And that's an important thing about sensation, and that's going to go across the board in most sensations. The last thing I want to mention about hearing is talking about really neat technology that exists for people who can't hear or have a very difficult time hearing with fairly profound hearing loss, and that is cochlear implants. Cochlear implants are surgical devices that are implanted in the internal ear that can help people who can't hear to actually make sense of sound and have a way to hear what is going on in the world around them. It's a good way for them to be alerted to things or even be able to understand speech in person or on the telephone. It's a small electronic device, and what they do is there's a portion that goes outside the skin. That's a transmitter with a microphone. And that is connected by a wire to a surgically implanted part called the electrode ray, and that electrically stimulates different regions of the auditory nerve. So it's creating the nerve signals that the cochlea would otherwise be creating, so that nerve signals make it from the auditory nerve or the cochlear nerve to the central nervous system, to the right parts of the central nervous system, so that the person who's using it can actually have some kind of hearing. It's not the same as hearing without it if you don't have hearing loss. It is different, and it does take the people time to learn or kind of relearn what sounds are being perceived as. But it does make a huge difference for people who otherwise would not have been able to hear anything or have a really profound hearing loss. It's not quite the same as a hearing aid. Hearing aids are a little different. Hearing aids, they amplify sound so that they play them really loud in someone's ears so that they can still stimulate the damaged parts of the ears. But the cochlear implants bypass the outer and middle ear. And that's kind of a really good thing for people with profound hearing loss because I think it's helped a tremendous number of people. The other thing I want to mention is a couple things you probably heard, like terms, and that is about ear infections. Typically, infections of the ear can happen in the outer ear, in the middle ear, or in the internal ear. The most common is the middle ear because bacteria from the auditory tube from the throat can get into the middle ear and cause an infection and inflammation and a lot of discomfort and pain in there. So you might have heard the terms otitis externa, otitis media, and otitis interna. Otitis means inflammation of the ear. So if the infection is causing external ear inflammation, it's otitis externa. If it's in the middle ear, otitis media, and if it's in the inner ear, otitis interna. Makes sense, right?
You buy a pair of socks, that's 2 socks. You buy a pair of Bombas socks, that's 4 socks. Because one purchased is one donated. Socks are the #1 most requested clothing item in homeless shelters. So when you buy a pair of super comfortable Bombas socks, you're also donating a pair. Bombas customers have powered over 150 million donations. So Bombas would like to thank you 150 million times. But we only have like 30 seconds. Go to bombas.com and use code AUDIO for 20% off your first purchase. That's BOMBAS.com and use code AUDIO at checkout.
All right, that's going to do it for hearing. In the next episode, we're going to stay in the ear and talk about equilibrium, and that will finish up the sensation topics for us and the nervous system for that matter. So I want to thank you so much for sticking with me. I hope this episode and all the episodes are helping you get that B or better you need in anatomy and physiology to move on with your clinical careers. So good luck, and I'll see you next time. Anatomy and Physiology Bit by Bit is a production of Minus 55 Media. Please take the time to rate the podcast, and don't forget to check out my YouTube channel Student Help for AP. That's Student Help, the number 4, AP. There's a whole lot of tutor videos on there that I think you're going to find helpful. Special thanks to my family, Bucks County Community College, and McGraw-Hill Education, where you can find Anatomy and Physiology Digital Suite, my low-cost, tutor video-based digital learning solution for anatomy and physiology, already being used at several colleges and universities.